examples of events. Okay, in the previous examples, I introduced probability spaces, various simple examples like tossing a coin, throwing a die, etc. In this lecture, we will use the same probability space, but we will start defining events on those probability space. You must have seen Professor Arvind's lectures where he defines events as subsets of the sample space. We will do a similar definition here, and then we will think about how to do set operations with events, how to do unions, intersections, complements, etc., and how to define further events in that fashion. So that's the main topic of this lecture. So let me begin with the first example of that we've been seeing so far. The first example is tossing a coin. I'll consider the slightly non-trivial case of tossing the coin, say 3 times. Okay, it's an easy enough example, but still rich enough that I can define some nice events for you. Okay, so if you remember the sample space, the outcomes, the set of outcomes, if you toss the coin 3 times, ends up being there are 8 possibilities: HHH, HHT, HTH, HTT, THH, THT, TTH, and TTT. Those are the 8 possible outcomes that you have if you toss the coin 3 times. Now I'm going to define some events now. The first event I will define, I'll call it E0. Okay, the event E0 in English will say that there were 0 heads. Okay, that's event E0. Similarly, I'll define an event E1, which is there was, right? It's not where, no. There was 1 head. Okay, then I'll define an event E2, which is there were 2 heads. And finally, I'll define an event E3, which is there were 3 heads. For each of these events, I'm going to write down the subset of the set of outcomes which specifies that. Now you can see there are 8 possibilities. If I say I want 0 heads, there's actually only 1 possibility that can happen here. So this is simply the subset TTT. Okay, any other outcome I pick, there will be at least 1 head, and E0 will not contain that. So now what about 1 head? There should be exactly 1 head. So that has 3 possibilities. You can have HTT, THT, and TTH. Okay, so there should be only 1 head. It could either be in the first toss, the second and third toss being tails, or the heads could be in the second toss, the first and third toss being tails, or the head could be in the third toss. So those are the 3 possibilities. Now we also have this E2, which is there were 2 heads, in which case you have these possibilities: HHT, HTH, and THH. Okay, so it's easy to see what these subsets are. And finally, we have there were 3 heads, and that's just 1 possibility. Okay, so these are these 4 simple events that one can define: E0, E1, E2, E3. Okay, so this is pretty common in most probability problems. You will have events defined as subset of the set of outcomes of the sample space. They will be defined in 2 ways. They'll usually be defined in English. There will be an English sentence which describes what the event is, and you will have to convert it into a subset or some understanding of what that subset would be. Okay, so that part is also very, very important. Now I can do further events. So here's another event in English, which is there was at least one head. Okay, so this is an interesting event. So I'm going to introduce a notation for it. I'll say E greater than or equal to 1. Okay, so this is there was at least one head in the outcome. Okay, so if you now look at this set, if you want at least one head, this is the possibility here. So you have HTT, this has one head at least, THT, TTH, and then you have HHT, HTH, THH, and then HHH. These are the outcomes. There are 7 possible outcomes in this event, which is there was at least one head. Okay, so now it's possible to write this event also as the union of 3 other events that we have before. We had these events E0, E1, E2, E3, and you can write this at least one head event as the union of E1, E2, E3. Okay, so remember, union, you have to interpret it as an OR, and what I'm saying here is the event that there was at least one head is equal to the event there was either one head or 2 heads or 3 heads, and that's easy to see why that's true. It's a very simple set theoretical logic there, and you can see that this is true. Okay, there's another event I'm going to define now. There was at most one head. Okay, so at least and at most have sort of opposite interpretations. There was at most one head means only one head must be there, or you could have no heads at all. Both of those are allowed. I could call this event as E less than or equal to 1, and then if you think about it, this is just either no heads or exactly one head, right? HTT, THT, TTH. Okay, now this again can be written as the union of 2 of these events, E0 union E1. Okay, so now this is, I mean, it's quite a simple experiment, so you can write down all the possibilities and unions and intersections, etc. But hopefully this is also illustrative. You're able to understand how these events are defined and how they work, etc. A few other things I want to point out about this E0, E1, E2, E3. If you take any 2 sets in this guy, and if you take an intersection, you're going to get the null set. Okay, because no 2 events in this among these 4 events will have any intersection at all, right? You can take any other possibility. You take E2 intersect E3, you will again get a null set, right? Why is that? I mean, if you can either have 2 heads out of 3 or 3 heads out of 3, I mean, you can't have both at the same time. So that's the intersection is clearly a null set, and also you can look at this sets and convince yourself that they really don't have anything in common and their intersection is null set. But if you look at the intersection of these 2 guys, E greater than or equal to 1 and E less than or equal to 1, okay, the intersection is not a null set. In fact, if you look very closely and write out all the things that are common here, you will see that you get E1 exactly. Okay, that also makes sense. These 2 events are what? It says one event says there's at least one head, the other event says there's at most one head. If you take the intersection, if you want both of those to apply, the only possible intersection is there was exactly one head. Okay, so you have these 2 events intersecting to give you E1. Okay, so these are the kind of examples where you think of events as subsets of the set of outcomes, and you look at unions, intersections, and all that. Okay, so we're going to see more examples just to illustrate these ideas. And this kind of an understanding of an event, breaking it up into unions and intersections, etc., is quite important. You'll see later on when you want to compute probabilities for these events, such kind of understanding of the events is very, very important. Okay, so let's move on to the next example. Okay, so throwing a die, we know that the outcomes are 1, 2, 3, 4, 5, 6. I could define a set, an event which says, okay, let's say the probability space is just throwing a die once. Okay, throw a die once. I'll take the first part to be thrown only once. So the outcomes is just this. The event which could be mildly interesting is the event that the number is even. Okay, what is this event? This event has the subset 2, 4, 6. Those are the 3 even numbers in this list. So that makes up the event that the number that showed up was even. Okay, so if you want, you can call it, I don't know, E even. Okay, so this could be the event. Okay, so nothing much more interesting in this example, maybe you could write down an event which is the multiple of 3, so which would have just 3 and 6, and then you can take the intersection of these two events, both even and a multiple of 6, so you would have just the number 6 showing up. Okay, so these are all examples, so maybe I should write that down. E mul 3 is number is multiple of 3, and that's just 3 comma 6, and then if you take the intersection, you simply get 6, right? So that's both even and a multiple of 3, that's just 6. Okay, so that's a simple example. So now let's say you throw a die twice. Okay, so now the outcomes are a little bit more, little bit bigger. You have 1 comma 1, 1 comma 2, so on till 1 comma 6. What does this mean? The first throw was 1, second throw was 1. 1 comma 2 means the first throw was 1 and the second throw was 2. 1 comma 6 means the first throw was 1, second throw was 6. So likewise, you can draw all the, you can write down all the possibilities here. When you throw a die twice, we'll go all the way to 6 comma 1, 6 comma 2, dot dot dot, 6 comma 6. This is the set of all outcomes when you throw the die twice. Okay, so this has got 36 possibilities in the set of outcomes, and you can define more interesting events. So for instance, I might want to define an event which says sum of the two numbers is let's say 6. Okay, so I could call this event as S6, which is the event that the sum of two numbers that you saw was 6. So now you have to think about how to write this down. So the first number could be 1, and if you want the sum to be 6, the second number has to be 5. The first number could be 2, and if you want the sum to be 6, the second number has to be 4. Or you could have 3 comma 3, or you can also have 4 comma 2. So I'm throwing it twice. I'm keeping track of which number came first, which number came second. So I can also have 4 comma 2. It's not the same as 2 comma 4, for instance. Okay, or you could have 5 comma 1. Okay, so these are the 5 possibilities in that you have for if you want the sum of the numbers to be 6. So let's say I also define similarly, let's say, I don't know, S10. Okay, so this says sum of the two numbers is 10. Okay, so here you don't have too many possibilities. For instance, if the first number were 1, you could never have anything for the second number to make the sum as 10. Okay, so the first number has to be at least 4 before you have a possibility of getting it 10. 4 comma 6, 5 comma 5, and then 6 comma 4. Okay, now you can also have other interesting events. You could have let's say E equal, which is two numbers are equal. This would have 6 possibilities: 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, 6 comma 6. Okay, and then you can start intersecting. You can intersect S6 intersect E equal, and S10 intersect E equal. You can start doing all these games, and you will get different possibilities. And then I might want to define more interesting events here. So you see that when you throw a die twice, you already get very many interesting list of events that you can make. So let me also now do other interesting events. So let's say I make this event S greater than or equal to 2. Okay, what is this event going to be? Sum of the two numbers is at least 2. Okay, this is what my event is going to be. Now I could start writing down all the possibilities. It's going to be a pretty big list, but one thing I can do is, I know that this is S2 union S3 union S4 so on till what is the maximum number I can get? S12. So the sum is at least 2, which means I get all these things. In fact, this list is in fact exhaustive. Okay, so this will be equal to the set of all outcomes. Okay, so in that case, this is a slightly trivial sort of event, but still, if you notice, the reason is, if you throw a dice twice, the least number is 1, so the sum of two numbers is at least 2. Okay, so it becomes the set of all outcomes. Maybe it's not so interesting. So let's look at something else. Maybe you might want to look at, say, s greater than or equal to 6. Okay, so this would be S7 union, I'm sorry, I should be careful here, that's S6. This event is S6 union S7 union S8 union S9 union S10 union S11 union S12, right? The sum of two numbers can start at 2 and it can go all the way up to 12. If you have 6, 6, you have 12, right? So that's the maximum sum possible. So if I say the sum has to be at least 6, I have to take S6 union S7 union S8 so on till union S12. Now there's a shorthand notation for these things. You don't have to keep writing these unions so many times. You can write S sub, say, I, and you can say I goes from 6 to 12. Okay, this is a very convenient shorthand notation to indicate that you're going to take unions of all these SIs starting from 6 going all the way up to 12. Okay, so now you can also define another event which I will call, now remember, what is this event in English? Sum is at least 6. This is the event. And define another event which will say sum is at most 5. Okay, so what is that? That is s less than or equal to 5. This would be what? S2 union S3 union S4 union S5. Okay, so I could also have a shorthand notation here, I equals 2 to 5 SI. Okay, so this looks like another interesting event. The sum is at least 5. It's S2 union S3 union S4 union S5. You can also have a shorthand notation which says union I equals 2 to 5 SI. Now there are some interesting things about this event. If you take the intersection of these two events, s greater than or equal to 6 intersect s less than or equal to 5, it's going to be the null set. Okay, so these two events we see clearly have a null intersection, and also interestingly, if you take a union of these two events, like I showed you before, s greater than or equal to 6 union s less than or equal to 5 will be the entire sample space omega. Okay, so this is the set of all outcomes. This is the standard notation for set of all outcomes that we have seen, the sample space. Okay, so if, for instance, if so quite often you might want to compute one of these probabilities, let's say s less than or equal to 5. If you compute the other probabilities, it will help out, etc. Okay, so knowing what the intersection is, or knowing what the complement is, all of that is very interesting. So for instance, here we see clearly that s less than or equal to 5 is actually the complement of s greater than or equal to 6. Okay, so these kind of relationships are very useful when it comes to computing probabilities. If you can compute the probability of one, it turns out you also know the probability of other. Okay, so what do I mean by complement? It means you have this set of all omega. If you intersect it with the complement of this guy, you get this. Okay, so this is also denoted in a very so this complement has this notation which is s greater than or equal to 6 complement, or people also denote it simply as just a c on top. In fact, this is the difference of omega and this set. Everything that is not in s greater than or equal to 6 will be in s less than or equal to 5, and we can see that clearly from this example. Okay, so these kind of interesting events can be defined just with the simple experiment of throwing a die twice. Okay, so you can imagine how more complicated it can get if you keep on throwing the die. Okay, so more and more interesting events can be defined. Okay, so let's keep moving ahead. The next event that I want to define is based on drawing a ball from an urn. Okay, so we saw before that the set of outcomes, let's say the urn has blue, black and red balls, and the set of outcomes simply is blue, black, red, right? That's the set of outcome. This is assuming we're doing one ball. Okay, so you have blue, black, and red being the outcome. You can have an event which is maybe, just a very simple event is the ball is blue, right? This is an easy event to write. But in case, let's say you draw 3 balls with replacement, without replacement, whatever you want, you can pick. So when you draw 3 balls, you already see that the set of outcomes is going to be, there are very many different possibilities. When you draw 3 balls, you could have a number of different possibilities. For instance, so let's say, let me also take a very specific case. Let's say there are 8 blue balls, 8 black balls, and let's say 9 red balls in the urn. Okay, so I'll take a very specific setting. I've taken these number of balls to be large enough so that the fact that I'm drawing 3 balls doesn't affect too much. So for instance, if there's only 1 blue ball, and if you're drawing 3 balls, you will only have 1 blue ball at the outcome. You can't have more than that. So I want all possibilities. So I'm doing these things. So I'll also have a shorthand notation. I'll denote blue as B, black I'll denote K, and red I'll denote R. Okay, just short form. So if you do this now, you have so many different possibilities. All the 3 balls could be blue. All the first 2 could be blue, next could be black. First 2 could be blue, next could be red, right? And then you can have blue, black, blue, blue, black, black, so on and so forth. I mean, so many possibilities are there. You can end up all the way in red, red, red. Okay, so how many different possibilities are there? There are 27 different outcomes. Okay, so we saw this earlier as well. I might be interested in the event E, which is draw 3 balls of different color. Okay, so I want the 3 balls that were drawn to have different color. Now, what is this? This is actually a subset of what we had before. How many different possibilities are there going to be there? It turns out you will have how many possibilities? The first thing could be any one, let's say blue. Next one has to be, let's say, black. Then you have red, or you could have black here. Black. I mean, you can't have 2 blacks, right? So I want all 3 to have different colors. Okay. Let's say you have black here, red here, blue here, and then red here, blue here, black here. Okay, so those 3 possibilities, and you will have 3 more. So for instance, you can have blue, red, and black. Okay, the ordering can be different, and then you can have black, blue, red, and then you can have red, black, blue. Okay, so these are the 6 possibilities that you will have if you want the 3 balls to be of different color. Okay, so you notice here it's just blue, black, and red, but since the 3 balls came one after the other and I know the sequence that's going to be different, I have 6 different possibilities. In case I did not distinguish the sequence in which the balls came, then all of this will collapse into just one possibility. Okay, so all these things are subtle in the way the problem is posed in English, so you have to pay a lot of attention and exactly translate it into what it means. Okay, so this is a couple of examples from drawing balls from urns. Okay, so then the next example I'm going to talk about is a card from a pack. Okay, so here again we know that the set of all outcomes has 52 possibilities. I gave you a notation for how to denote these things. You can have 2 of spades all the way till ace of spades, and so on till 2 of diamonds till the ace of diamonds. Right? You have 4 suits, and then 13 different cards in each suit. You can have all these possibilities come up. So that's omega. You can have different events now. The event ES could be that the card was a spade. Okay, so this will have 13 different possibilities, 2, 3, all the way till ace of spades. Okay, 13 possibilities here. Okay, you could have, say, EK, which is card was a king. Okay, so this is, once again, I should tell you, this is I'm drawing one card. Okay, this is what can happen. Okay, so if you say card was a king, it could be the king of spades, king of clubs, king of hearts, or king of diamonds. There are 4 possibilities. Okay, if you want an intersection here, this will simply be king of spades, right? So card needs to be a spade, and card needs to be a king also. There's only one card like that, that's king of spades, and you could even call this event as EKS. Okay, there's only one event there, king of spades. So this is all that you can do kind of with drawing one card. Now, quite often in many card games, you won't be drawing just one card, maybe you're drawing 3 cards. 3 cards, let's say without replacement. If you want to be very specific, you're going to draw 3 cards. Okay, and one of the interesting things that people ask is, so now first of all, if you draw 3 cards without replacement, okay, your outcome set is going to be quite large. Okay, so you will have 52 possibilities for the first card times 51 possibilities for the second card times 50 possibilities for the third card, right? So this is the sequence in which it can come. This is a pretty large number. I'm not going to be able to list it for you. If you want, you can say, for instance, you could have 2 spades, 2 clubs, 2 hearts, okay, all the way till maybe the last one is ace of clubs, ace of hearts, ace of diamonds, right? So you will have all the 50, 52 times 51 times 50 possibilities listed out in the set of all possible outcomes. Okay, so you might ask the question, for instance, an interesting question is, I'll call it E sequence. Okay, the 3 cards are in a sequence. Okay, quite often when you play a game, this is quite important. I mean, if you got 3 cards and all of them are in a sequence, then maybe that's a good hand, you know. I mean, quite often games have this kind of a requirement, and you can try to compute the probability of this, or you can, if you want to compute the probability of this, eventually first you have to understand this event, how many possibilities are there in this event. Okay, so 3 cards in a sequence means the event here is also pretty big, you know. I mean, you can have, let's say, 2 spades, 3 spades, 4 spades in an event, or in fact, you know, the same thing can occur in any order. You could have also got 4 spades, 3 spades, 2 spades, or you could have got 3 spades, 2 spades, 4 spades. In fact, you will have 6 different possibilities for every possible sequence, right? It can come in any order. And then how many such sequences are there? It can go on and on and on. It's not very clear how to do it. In fact, even in spades, you can go up to queen spades, king spades, ace spades, and then on and on and on. I mean, so many possibilities are there, right? In all the different orderings in which you can get it, right? So the last one maybe is, queen of diamond, king of diamond, ace of diamond. Okay, so this is quite a big event. Okay, just drawing 3 cards from a pack, and if you want to ask 3 cards are in a sequence, the event becomes really, really big. Okay, so what I want to highlight here also when I start giving these examples is, if you just start always thinking about the total number of possibilities and then reducing the event into a subset of that total number of possible outcomes, you will soon run into difficulties. For small examples, you can write down the events very nicely as subsets and intersections and all that. Once the examples start becoming more and more complicated, you have to have a different way of understanding these events, okay, so that your calculations and all that will become easier. So as we go forward, we will look at those kind of methods. The methods such as independence, conditional probability, all of these will help you understand these kind of large event spaces, large probability spaces, break them down into smaller parts, and then do computations. Okay, so hopefully you saw that this 3 cards in a sequence is quite a bit complicated. Later on, we'll evaluate probabilities for this, and you'll see there are easy methods to get around these difficulties. Okay, but listing out all possibilities is definitely not a very interesting or useful method for problems of this type. Okay, the last example I want to see, we'll close with that, is balls into pins. To be specific, I'll consider 10 balls into 5 bins. Okay, so once again, let me draw the 5 bins for you. 1, 2, 3, 4, 5. And remember, the balls are not going to be distinguished and I'm not going to bother which ball went first, which ball went second and all that. Okay, so all those things I'm going to consider. So finally, my outcomes are only the number of balls in each bin. This is the only thing I'm concerned about, at least at this point. Okay, I don't want to care about in what sequence the ball went. I'm not going to distinguish the balls, all of them are the same. I just throw them and then I observe. Okay, so my outcomes are number of balls in each bin. Okay, so we saw that one way to represent this is to look at this vector n1, n2, n3, n4, n5. Each ni is from 0 to 10. Okay, and then summation of the ni, I equals 1 to 5 has to be equal to 10. Okay, so this is the condition, right? The number of bins, so ni is basically the number of balls in bin I. Is that okay? So the first bin has n1 balls, second bin has n2 balls, etc. We know that each bin might either have 0 balls or 1 ball or all the way up to 10 balls. Okay, because I threw 10 balls. And the total number of balls is only 10. Okay, so if you add up n1 to n5, you should get 10. Okay, so that's the condition. And it's kind of difficult to enumerate this. One needs to be a little bit clever in coming up with methods for thinking about this space. Okay, let me write down simpler events here. So I might be interested in the event, let's say a lot of events are interesting. So for instance, I might be interested in the event that I could call it, say, 1, 2, which is bin 1 has 2 balls. Okay, so I'm interested in all the outcomes in which n1 was 2. Okay, so this doesn't really simplify anything. So you'll have to think of, put 2 here, and then what will you put here? N2, N3, N4, N5, and you still have to write all these possibilities. 0 less than or equal to ni less than or equal to 10, and then you have N2 plus N3 plus N4 plus N5 equals 8 now. Okay, so it's quite a big set again. You can't really simplify the event significantly. In fact, some events which are interesting is E10, which is what? Bin 1 is empty. Okay, so bin 1 is empty is again has basically 0, N2, N3, N4, N5. Again, you can't do much more about this, right? So 10 and then N2 plus N3 plus N4 plus N5 is 10. Okay, this is bin 1 is empty. Okay, so you can also have similar events like E20, which is bin 2 is empty, E30, which is bin 3 is empty, bin E40, E50, like that. Okay, you can have these kind of events. And then, even though you don't know much about these events, I mean, if you start listing it out, it's quite big. There are some some sort of a symmetry going on here. So for instance, you can think, if you think about it very carefully, the number of entries in E10 and the number of entries in E20 will be the same, right? The number of outcomes that make bin 1 empty, the number of outcomes that make bin 2 empty are the same, right? So you can kind of argue, even though you don't know much about these events exactly, you can kind of argue that they will be similar, and this is all quite useful. Okay, so in fact, if you do intersections, you will get interesting possibilities. Let's say I start intersecting E10 and E20. Okay, so I want to look at all the outcomes where bin 1 is empty and bin 2 is empty, right? So that will be a set like this: 0, 0, and 3 and 4 and 5. 0 less than or equal to ni less than or equal to 10, and then n3 plus n4 plus n5 equals 10. Okay, so again, quite a big possibility here. It turns out, if you keep on intersecting, you will eventually get to something which is easy to think about. Okay, suppose I intersect all 4 guys. Okay, I want bin 1 to be empty, bin 2 to be empty, bin 3 to be empty, bin 4 to be empty, which means what? All the balls went into bin 5, okay, and that is just one possibility. Okay, isn't that nice? So till you do a lot of intersections, you don't get simple outcomes. Maybe one can also enumerate this case without too much difficulty. If you enumerate E30, this is just we want bin 1 to be empty, bin 2 to be empty, bin 3 to be empty, bin 4 and bin 5 can be non-empty, but they have to sum up to 10. Okay, so you should have a slightly easy possibility here. You could have 0, 10, or you could have 0, 0, 0, 1, 9, so on till 0, 0, 0, 10, 0. Okay, so you have 11 possibilities here, I think. Yeah, 11 possible outcomes here. Okay, so hopefully you see that these kind of problems are interesting, and quite often when the sample space becomes big, you're not going to be able to write down the exact event as an exact subset very easily, but still you can do something clever arguing based on what the structure of the problem is. So for instance, one of the questions that's interesting is no bin is empty. Okay, so this is an interesting event. Okay, so you might be interested in this event. If you want to look at no bin is empty, what will be that event? Okay, so you want to look at E10 complement. First bin is not empty. Intersect it with E20 complement. Second bin is not empty. Intersect it with E30 complement. Third bin is not empty. Intersect it with E40 complement. Intersect it with E50 complement. Okay, all the bins are not empty. Okay, no bin is empty. So we have this interesting event that no bin is empty, and we're able to write it as the intersection of 5 different events here: E10 complement, E20 complement, and so on. In fact, you can use these De Morgan's laws, and you can also write it as the whole complement of something. So in fact, you can also write it as E10 union E20 union E30 union E40 union E50, and then whole complement. Okay, so we know these two are the same, and this also makes sense. What is the event inside this complement here? E10 union E20 union E30 union E40 union E50. This, what is inside, is what? At least one bin is empty. At least one bin is empty. Okay, that's the event which is inside the bracket. And then if you take complement, what will you get? No bin is empty. Okay, so this is an illustration of how De Morgan's law works. Okay, so we'll look at this this kind of a breakup of this event, and you'll see it's interesting to ask questions like this. You might also ask other questions. You might say exactly one bin is empty, exactly two bins are empty, things like that. You might also want to ask. All those problems are complicated. Okay, so we saw in this lecture that we went from very simple experiments, very simple events and easy understandable things, to slightly more complicated events where already the sample space is very large and the event space is very large, and you have to think and argue very carefully about what can happen. But still, the tools of probability will help you as you learn more in the coming weeks, that such complicated events you can still work with and compute probabilities as you go along. Okay, thank you very much. That's the end of this lecture.